get going. So with that, I think I'll turn it over to Sam. Sam is right now a postdoc at CITA up at Toronto. And he's going to be discussing his celmech code that he has put together and published on EMAC. So take it away, Sam.
Thanks. Yeah. So, like Bobby said, I'll be talking about relatively new code, celmech. I developed this in collaboration with Dan Tamayo, who's now at Harvey Mudd, as well as some input from David Hernandez, who's now a postdoc at Yale. So what is it? Celmech is a sort of all-purpose code for lots of different celestial mechanics calculations. It has a lot of functionality, and a lot of which I won't be able to touch on today, but the sort of bread and butter capabilities are things like calculating disturbing function expansions, constructing, manipulating, and integrating Hamiltonian equations of motion for planetary systems, and lots of other things. If you don't know what those things are, I hope it's also a nice learning resource for people sort of unfamiliar with doing celestial mechanics as well. It's developed mainly in Python, and one of the key features of the code is that it's designed to work closely with the popular rebound n-body code, which I know is quite popular, but if you haven't had a chance to use it and you find yourself needing to run n-body integrations, I highly recommend. And celmech is also built on top of a very powerful symbolic mathematics library in Python called SymPy. And so another practical points, where is celmech? You can download it using pip. It's on PyPI, so pip install celmech will install it. You can get the bleeding edge version from the GitHub repository, where I've also included lots of Jupyter notebook examples in a similar spirit to Rebound. If anybody's ever been on the Rebound GitHub, they know it has lots of helpful examples for getting started on different problems. There's extensive documentation on a read the docs page. And like I said, I've tried to make this a learning resource as well. So I've tried to make the documentation fairly pedagogical for people who are sort of interested in doing celestial mechanics calculations, but never have done it themselves before. I've even put this notebook up on GitHub. I'll put a link somewhere in Slack if people want to follow the links. And if you're a real glutton for punishment, you can go try to read the paper in AJ, or watch me prattle on about it in a AAS Author Journal Series video, if that's what you're into. Anyway, so just in the remaining time, I'll try to give a sort of overview of the basic principles of the code. So n-body codes like Rebound, for example, are designed to solve the exact equations of motion of an n-body system like a planetary system. And it does this by constructing numerical solutions to a set of ordinary differential equations. These are usually formulated in terms of the positions and momenta of the star and planets in the system, and just integrates the gravitational force between pairs of bodies in the system. And this is nice for sort of getting exact numerical solutions, but it's hard to make much headway for doing any sort of theory from these sorts of equations of motion. And what celmech is designed to do is to get approximate equations of motion to that are designed for sort of working out analytic or semi-analytic theory. And the sort of general way this game is played is that one constructs approximate equations of motion from a so-called disturbing function expansion of the Hamiltonian governing the system. So what this looks like is you expand the gravitational interaction potential between pairs of bodies in a multi-infinite series that's a cosine series in the orbital angular elements, like the mean longitude, longitude of periapse, and longitude of ascending node, shown here in the cosine argument, and a power series in eccentricities and inclinations, which are typically small. This is a sort of foreboding looking expression, and you haven't really made any progress if you're working with multiply infinite sums. But the way one makes progress taking this approach is to usually you can select just a few important dynamical terms from this multiply infinite sum to construct a model that often allows you to get theoretical insights into the problem that you're looking at, and allows, in many cases, a system of equations that you can integrate much faster than the full dynamical n-body equations. Okay, so that's a bit abstract. Maybe it's best illustrated by way of an example. So I'll just go through a quick example that sort of demonstrates how one might work with celmech. Like I said, it's designed to work closely with rebounds. So we'll start by making a rebound simulation. And for our example, we're gonna stick a pair of Earth mass planets around a solar mass star in a 3:2 mean motion resonance. So in the cell that I'm showing here, I've initialized a rebound simulation, and I'm adding each constituent of the system. I add the star with a solar mass and then a pair of Earth mass planets. And you can see I put their periods at a ratio of 3:2 and given them some sort of arbitrary initial eccentricities and angular orbital elements, and we get a nice graphical representation of our system here. And so we can take our rebound simulation and use it to initialize the elements that we'll be using to make our celmech model. So I'm importing two of the basic workhorse classes of celmech in the slide, the Poincare and Poincare Hamiltonian classes. And I can instantiate an instance of this Poincare class directly from our rebound simulation that I made earlier. And then I can use this to go on and instantiate an example of our Poincare Hamiltonian class. And I'll say a little bit about what each of these classes are. So the Poincare class is used to represent the dynamical state of the system. So just like you would store masses along with coordinate positions and velocities in an n-body system, the Poincare class stores this information. However, it uses canonical action angle variables since we're using a Hamiltonian formulation of the equations of motion internally. So it stores both symbolic parameters for the canonical variables as well as their numerical values. The set of variables it uses is this capital lambda, which is related to the semi-major axis degree of freedom and is conjugate to the mean longitude. And then there's pairs of canonical coordinate momentum variables that are related to the eccentricity and inclination degrees of freedom. And you can see under this QP pairs attribute, we have pairs of coordinate and momentum variables stored symbolically for each planet. So planet 1 and planet 2 in the system that we set up. And like I said, it also stores numerical values for these variables, which is inherited directly from the rebound simulation. So it sets the numerical values automatically when you inherit it, when you instantiate it from a rebound simulation. The Poincare Hamiltonian class is the other object that we initialized, and this is designed to represent the Hamiltonian governing the system's evolution that we'll be modeling. So it has an attribute called H, which just stores a symbolic representation of the Hamiltonian. Here you see it depends on our canonical variables, these capital lambdas, and then there's a bunch of parameters that enter the expression as well. And upon initialization, we just have the Hamiltonian governing non-interacting Keplerian orbits. This is a bit confusing, but if you rewrote this in terms of orbital elements, it would just be the Keplerian energy of the two planets' orbits with semi-major axes A1 and A2. And the way one typically works with a celmech model is by building up some Hamiltonian by selecting and adding individual disturbing function terms. There's all sorts of ways to do this. We'll use a nice convenience method in our example here to add terms related to the 3:2 mean motion resonance. So this is just a one-line call. We're adding terms associated with our 3:2 mean motion resonance, giving interactions between the inner and outer planet. And after we do this, our symbolic Hamiltonian that we've stored is updated with new terms. And you can see some of our other canonical variables appearing in this symbolic expression. It's a bit busy to look at in these variables, but you can get a symbolic representation in terms of orbital elements too under this DF feature. So that's shown here. And this will be familiar to anybody who's done these sorts of calculations before or been through Murray and Dermot, for example, the textbook. Okay, and so now that we've built our simple dynamical model with CELMech, we can use it to integrate Hamilton's equations of motion. And the integration interface is designed to mirror rebounds pretty closely. So I've set up a simple loop where we'll integrate over a series of times for 2,500 orbital periods of the inner planet. And you can see we make calls to this .integrate method for both our rebound simulation and our CELMech model, which was stored in HP to advance the state of the system. And at each time through the loop, we're storing the resonant angle at that time. And we can plot the evolution. So now I'm taking those resonant angles that I stored in that loop, given by this combination of mean longitudes and the longitude pericenter for the inner planet. And you can see we get good agreement a fairly good agreement between rebound and CELMech. One can go on to explore adding higher order terms to see if that gives better agreement, but that's the sort of basic gist. I'm low on time, so I think I'll stop here and just say that there's lots more that I don't have time to cover. In 10 minutes, everything from canonical transformations, Laplace-Lagrange theory, anything you could hope to do with mean motion resonances. So thank you.
Thanks a lot, Sam. I think everyone can see the reactions at the bottom for claps and high fives and things. So let's give Sam a clap. Hooray. So, okay. So we have time, a few minutes for questions here, 3 minutes here, and please raise your hand, as we said, down at the bottom. We have first question from Aviv up here.
Hi, Sam. Very nice talk. Thank you. How do you see it used? Because you were a little bit technical on what it does, but how is it going to be used? How can I use it?
It's hard to come up with just one answer because I think there's lots of applications. So one thing that I'm currently using it to explore is secular chaos and long-term evolution of planetary systems. So rather than lots of Kepler systems, for example, have orbital periods, of order 10 days. And so running multi-billion year integrations by direct n-body is not really feasible, but you can get the equations of motion governing the secular dynamics of the system, and those can be integrated more efficiently since the dynamical timescale is much longer. So that's one example. Exploring capture into mean motion resonance is another application. You can use it to generate transit timing variations, sort of all sorts of dynamics questions that one could hope to address.
Thank you.
Sure.
Thanks, Viv. Any other questions for Sam here?
This is Mark Elowitz. I just had a quick question. Does it include relativistic effects?
They can be, yes, yeah, if you want to add them in. So general relativity, sort of at the lowest approximation, causes perihelion precession.
Yes, yeah.
And you can add, that can be put into a Hamiltonian model of the sort that CELMech works with a simple, including a single term. And yeah, there's an option to add that.
Okay, thank you.
Sounds good. Well, if there aren't any further questions, of course, can be into the Discuss Talks channel. Sam, you can check that out. And then let's move over to the next slides.